Let's determine the following limits, or end behavior of the following polynomials. Notice these examples or these functions are very simple polynomials. You may have even recalled their end behavior in a pre-calculus experience. For example, the first function here is actually a parabola that is facing down. So you may actually know the end behavior for this function. There it is, right? The end behaviors, both ends of that function is actually pointing downwards. So you would actually think it's negative infinity. For this example here on the right, what is the opposite cubic function? This is approximately that, right? So then you know the left end is actually pointing up and the right end is pointing down. And so you could actually gather, similar ends just by using your algebra experience, knowing the even or odd powers of the polynomial term with the highest degree. Okay, let's look at that term with the highest degree, and let's try to evaluate this using algebra. But this algebra is unusual. It's what I call fake math, or in some ways, you could lump it into conceptual math. Okay, so if you think about this, if you write this in descending order, we'll write the first term that has the most power, meaning the greatest exponent, and that's what we're going to concentrate on. I want you to concentrate on this opposite of x squared. Everything else actually has very little meaning, simply because it's not going to take on too much of a value or too great of a value if x is approaching very large in the negative direction. So as x is approaching very large in the negative direction, what we can do is estimate the end behavior here by looking at that leading term with the highest degree. So all I'm going to do is put in the concept of opposite of very large squared. So what's very large squared? It's still very large, and then of course take its opposite direction. So do order of operations, take very large, square it, you still get very large, and then you take its opposite direction. So that means this limit, not surprisingly, is actually negative infinity, and it matches your algebra experience. We could do a similar thing with the second example here. I want you to focus on this opposite of x cubed term. And notice if you add 1 to a very large number, it's not going to make a huge difference. So I call this bubble math because it's conceptual math. And so we're going to take this opposite, and then we're going to take that very large and raise it to a third power. Now this very large means the concept of infinity. So what happens when you take a very large number and raise it 3 times? Imagine 1 billion and then cube it. Okay, what's a billion cubed? Is that a very small number or a very large number? It certainly is very large. Okay, so then take its opposite. So we have it. We actually have this end behavior here. And it's actually going to be negative infinity. And notice it matches your intuition of the opposite of x cubed, just like you had in algebra. Just like the first example is a what? Downward parabola, and you can actually see the end behavior. So using this conceptual math, we could gather end behaviors. Let's check its form. So one way to understand limits is by checking forms. What's 40 times very large raised to the 98th power plus very large raised to the third power? You could see that this is really what? It looks like very large plus very large, which is a determinate form. It's going to be determined to be the concept of infinity. So here, once again, you could focus on the leading term with the highest exponent and realize that if you add x cubed relative to x to the 98th, it doesn't mean a whole lot. So even right here, even this would be adequate. What's 40 times very large raised to the 98th power? It's still very large. So this is obviously going to be very large. Once again, the limit does not exist, but you could see that the end behavior is going to be approaching infinity. We'll do a similar thing here. We'll focus on that first term with the highest exponent. We're just going to focus on x to the 97th. And if you take away 2x, it doesn't mean a whole lot relative to the 97th power. So let's look at the conceptual math here. This is just going to be 16 times very large raised to the 97th power. Well, if you write in the words very large and raise it to the 97th power, you're still going to get a very large number. Then multiply that very large number by 16, you're still going to get a very large number. So it's obvious that the end behavior is going to be, oops, I'm sorry, I forgot a negative sign here. Let's put the negative sign there. That does change things. What's a negative number, or negative very large number raised to the 97th time? That will be negative very large. So this will be 16 times negative very large. What do you get? You still get negative infinity. That is not a finite number, so you can remember that you could conclude that this limit does not exist, but you are able to describe the end behavior. Now, why do you need to learn how to use concepts of infinity? Well, it's because that's how you evaluate other limits, especially rational functions. So with rational functions, you will need an additional theorem. You'll need this theorem here. So when you pay close to this theorem, when you pay close attention to this theorem, you're going to realize that this 1 is insignificant. This 1 could be 6. It could be 600. This 1 here could be 8,092. Then this conclusion of 0 will still exist. All right. So how do we evaluate rational functions? We look at the degree of the polynomial in the numerator and look at the degree of the polynomial in the denominator and do an algebra trick. And this algebra trick will consist of multiplying by a magical 1. You will take that highest exponent and put it 1 over x squared. And then if you're going to do that to the numerator, you have to do it to the denominator. And we're going to multiply. And we'll use the theorem above. Now, what does this mean? We're going to check its form. I should have told you that I checked the form in the previous step, but if we check the form on this step, you're going to see the concepts are really important. Because what's 1 over very large quantity squared? That's going to get you very small. We'll symbolize very small with the number 0. So very small minus very small minus approximately 1, right? Because the first two numbers are actually just very small. Over what here? 2 minus very small. And so this is a determinate form. And in fact, this is really getting close to what? Very, very, very close to negative 1/2, which also matches your experience from algebra. That is, in fact, how you conclude a horizontal asymptote from your algebra. But using the definition in calculus, we could actually conclude that, therefore, a horizontal asymptote is y equals negative 1/2. Remember, you have to say y equals negative 1/2 to conclude the horizontal asymptote. Now there is some work involved. You do have to do that magical one trick here. Let's do the magical one trick. In the second example, I'm going to multiply this time by 1 over x to the higher degree. The higher degree is to the third power. The other degree is just degree of 1. So we always do this with the higher degree. Okay, you analyze the degree of the numerator versus the degree of the denominator in rational functions, and we do this magical trick when we talk about end behavior of rational functions. We'll go ahead and write the algebra. The limit as x approaches infinity, and now we have a function that we will analyze as negative 1 plus 1 over x to the third power over 2 over x squared plus 8 over x to the third power. I'm going to check its form here. I should have told you I did check the form earlier. The earlier form was actually negative infinity over infinity, which is indeterminate. Okay, if you check the form on this line, this is actually getting very close to negative 1 plus something very small over what? Very small plus very small. Now be careful here. The denominator here is not 0. These are conceptual. So it's almost better to write negative 1 over very small. What's negative 1 over very small? That is going to be very large in the negative direction. Okay, if you don't believe me, take this example. Take negative 1 and divide it by something very small. You could do this on your calculator or just use scientific notation and see what you get. You'll realize you're going to get something very large, but in the negative direction. And there you go. There it is. So that is the work to evaluate this limit. Now this limit, because it approaches negative infinity, it also does not exist. One more example here. Let's compare the degree of the numerator with the degree of the denominator, which one's higher, and then we do the magic trick. Once again, I already checked its form. I know I'm doing this quite fast, but the form on the first line is actually going to be what? Just from the previous page, you'll see that that's infinity over infinity. You know that is indeterminate. You cannot conclude anything there. You cannot call that 1. That's certainly not 1 because very large over very large is undetermined or indeterminate. Okay, indeterminate. So we're going to perform this magic trick and simplify. Algebra is a form of magic. So we get something that's close to 40 over 1 over x to the 95th power. And if you check the form on this line, you'll realize you're not having very large over very large anymore. Instead, you have something approximately 40 over something very small. Now, what's 40 over very small? That's got to be very large. Okay, just from the previous example there, you're going to realize, oh, that's going to be very large in the positive direction, and you're done. So that would be the work to evaluate that limit.